Welcome to Fluid Kinematics. This topic discusses fluid kinematics, which focuses on how fluids move without directly considering the forces causing the motion. The main focus is on describing velocity fields, particle paths, and different methods of flow visualization. This approach is essential as a foundation before entering force-based fluid dynamics. By understanding motion patterns, different types of flow and their behavior can be classified. This chapter serves as a bridge between basic fluid concepts and momentum and energy analysis.
Lesson Plan: Fluid Mechanics I. The course structure is arranged progressively from basic concepts to more complex flow analysis. Early chapters discuss fluid properties and statics, followed by kinematics and energy equations. This sequence ensures a logical and systematic development of understanding. Fluid kinematics is placed before Bernoulli and momentum analysis because it forms the foundation for describing flow. With this roadmap, students can clearly see the role of kinematics in the overall course.
Learning outcome. The learning outcomes emphasize the ability to understand two main ways of describing flow, namely Lagrangian and Eulerian approaches. Students are also expected to distinguish various flow visualization methods, such as streamlines, path lines, and streak lines. The concept of fluid deformation and the difference between rotational and irrotational flows are key topics. Vorticity is introduced as a measure of local fluid rotation. The Reynolds transport theorem is presented as a tool linking system and control volume analyses.
Tracking objects in systems. Systems with a small number of objects, such as billiard balls, allow very precise tracking of individual motions. Limited interactions make the system behavior easier to predict and analyze. The computational complexity is also much smaller compared to systems with many particles. This approach is suitable for rigid body or discrete particle mechanics. However, it becomes impractical when applied directly to fluids composed of an enormous number of particles.
Lagrangian description. The Lagrangian approach follows the motion of each individual fluid particle over time. The position and velocity of each particle are recorded as functions of time. In this way, changes in fluid properties can be analyzed along the particle path. This approach is very intuitive because it resembles tracking objects in classical mechanics. However, for real fluid systems with an enormous number of particles, this method becomes computationally inefficient.
Check your understanding, question number 1. This slide is a concept check question about what is actually tracked in the Lagrangian approach. The key idea is that this approach monitors the position and velocity of individual particles. By answering this question, the distinction between particle tracking and field observation becomes clearer. The question reinforces the main focus of the Lagrangian description. This part is not discussed further here as instructed.
Eulerian description. The Eulerian approach does not follow individual particles, but observes flow properties at fixed points in space. Velocity, pressure, and other properties are expressed as functions of position and time. This method is much more practical for engineering analysis because there is no need to track particles individually. An example is measuring airspeed using a probe at a specific location. This approach forms the basis of field equations in fluid mechanics.
Velocity field and streamlines. The velocity field describes the flow velocity at every point in space at a given time. Velocity vectors show the local magnitude and direction of the flow. Streamlines are curves that are always tangent to the velocity vector at every point. The pattern of streamlines helps visualize the overall flow structure. A stagnation point appears at a location where the flow velocity becomes zero.
Flow field at dam inlet. A specific region of the flow field can be modeled to simplify the analysis of complex flows. Near the dam inlet, streamlines show how the flow converges toward the intake. This approach allows the use of a portion of a previously known velocity field to approximate local flow behavior. In this way, engineering analysis becomes more practical and manageable. This example shows how kinematic models are used in real applications.
Newton's law for fluid particles. Newton's law is used to explain the relationship between force, acceleration, and the motion of a fluid particle. The acceleration vector is always aligned with the resultant force acting on the particle. However, the velocity direction does not have to be the same as the acceleration direction. This shows that a particle's trajectory depends on its motion history, not only on the instantaneous force. This concept forms the basis for deriving the equations of motion in fluid mechanics.
Check your understanding. Number 2. This question emphasizes the relationship between force, acceleration, and velocity in particle motion. The core idea is that acceleration aligns with the force, while velocity may have a different direction. This is important to understand why particle trajectories can be curved. The question reinforces the different roles of force and velocity in dynamics. This part is not further developed here, as instructed. Fluid particle motion. The motion of a fluid particle is analyzed by decomposing its velocity into directional components. In many cases, a two-dimensional analysis is sufficient to describe the flow behavior. The particle position changes with time according to these velocity components. By tracking these position changes, the particle trajectory can be determined. This approach connects kinematic description with the geometry of the flow path. Fluid acceleration in steady flow. Steady flow does not necessarily mean that the particle velocity is constant along its path. Inside a nozzle, fluid particles can experience acceleration even though the flow does not change with time. This happens because of changes in the flow cross-sectional area. The velocity increases as the fluid passes through a converging section. This example shows that acceleration can arise from spatial changes, not from time variation. Residence time in nozzle. Residence time indicates how long a fluid particle takes to travel from the inlet to the outlet. This time depends on the path length and the velocity distribution along the nozzle. The concept is important for analyzing processes that depend on contact time, such as reactions or heat transfer. By knowing the residence time, particle behavior can be predicted more accurately. This is an example of applying kinematics to practical analysis. First-order finite difference. A derivative can be approximated by dividing the change in a quantity by the change in the independent variable. This approach uses small segments that are assumed to be linear. In this way, a curve can be approximated without using complicated calculus. This method is widely used in numerical analysis and discrete approximations. The concept also helps in understanding the physical meaning of a derivative. Check your understanding. Number 3. This question tests the understanding of the basic idea behind the first-order finite difference approach.
The key point is dividing the change in the dependent variable by the change in the independent variable. This reinforces the meaning of a derivative as a rate of change. The question also connects the mathematical concept with its physical interpretation. This part is not further developed here, as instructed.
The material derivative follows the change of a property along the path of a fluid particle. This concept combines the effects of local time variation and the motion of the particle through the flow field. With this derivative, particle acceleration can be expressed mathematically. This approach unifies the Lagrangian and Eulerian viewpoints. The material derivative becomes a key concept in fluid dynamics. The components of material derivative consist of two main parts, namely the local time change and the advective change. The local term represents the change at a fixed point in space. The advective term represents the change due to the particle moving through the field gradient. Together, these two components give the total change experienced by the particle. This separation helps in understanding the origin of acceleration in fluid flow.
Flow visualization around spinning baseball. Smoke visualization is used to observe the flow pattern around a spinning baseball. The interaction between the flow velocity and the ball's rotation produces complex vortex patterns. This phenomenon shows how rotation affects flow separation and vortex formation. These aerodynamic effects are very important in determining the ball's trajectory. This example highlights the role of visualization in understanding real flow behavior.
Streamline and velocity relation. A streamline is always tangent to the local velocity vector at every point in the flow field. This relationship shows that the instantaneous flow direction can be directly read from the shape of the streamline. In two-dimensional flow, small position changes can be expressed in terms of dx and dy along the curve. This concept links the geometric representation of flow with the velocity vector field. Therefore, streamlines become a very powerful visual tool to understand flow direction.
Streamlines and velocity vectors. Streamlines are drawn as continuous curves that represent the flow paths in the velocity field. Velocity vectors are shown as arrows indicating the magnitude and direction of the flow at specific points. When both are displayed together, the flow structure becomes much clearer. This pattern helps compare flow direction and intensity at different locations. This combined representation is very commonly used in flow analysis and visualization.
Check your understanding. Number 4. This question emphasizes the combined meaning of streamlines and velocity vectors in flow visualization. The key idea is that together they show flow paths and the magnitude and direction of velocity. This concept is important to avoid confusing flow visualization with actual particle trajectories. The question reinforces what is really represented by a flow field picture. This part is not further developed here, as instructed.
Stream tube characteristics. A stream tube is formed by a bundle of adjacent streamlines that enclose a flow region. Fluid inside the stream tube cannot cross the imaginary walls formed by these streamlines. Therefore, the flow inside a stream tube can be analyzed as a single entity. The cross-sectional area of the stream tube can change according to changes in flow velocity. This concept is very useful for visually explaining mass conservation.
Stream tube in incompressible flow. In incompressible flow, acceleration of the flow causes the stream tube cross-section to contract. Conversely, deceleration of the flow causes the stream tube cross-section to expand. This change in shape is a direct consequence of mass conservation. Even though its shape changes, the fluid remains within the same stream tube. This example provides a clear geometric picture of the relationship between cross-sectional area and velocity.
Pathline characteristics. A pathline is the actual path followed by a fluid particle over a certain time interval. This curve shows the particle position from the initial time to the final time. With pathlines, the motion of individual particles can be studied in detail. This concept is closely related to the Lagrangian approach. Pathlines are very useful for understanding particle behavior in unsteady flows. Pathlines in wave motion. With long exposure photography, particle paths in waves can be visualized as elliptical curves. This shows the difference between wave propagation and actual fluid particle motion. This visualization helps avoid misconceptions about mass transport in waves. This example emphasizes the importance of pathlines in periodic flow analysis. Check your understanding. Number 5. This question emphasizes that particle paths in waves are elliptical and are related to wave dynamics. The purpose is to reinforce the understanding of the difference between particle motion and wave propagation. By answering this question, the concept of pathlines in periodic flows becomes clearer. The question also connects visualization with physical interpretation.
Wingtip vortex analysis. Wingtip vortices are formed due to the pressure difference between the upper and lower surfaces of a wing. The color contours show the distribution of normalized local vorticity. Vector arrows illustrate the direction and pattern of fluid motion in the measurement plane. This pattern reveals strong rotational flow structures behind the wing. This example shows how the concept of vorticity is used in aerodynamics.
Streakline formation. A streakline is formed by continuously injecting dye or smoke at a fixed point. The traces of the released particles form a curve that shows the history of the flow. The shape of a streakline can change when the flow passes around or interacts with an object. This visualization is very useful in experiments to observe real flow patterns. A streakline provides a time-integrated picture of the flow. Streaklines in steady flow. In steady flow, streaklines, streamlines, and pathlines coincide and become identical. This happens because the velocity field does not change with time. The injected dye follows the same path as the instantaneous flow direction. This condition greatly simplifies the interpretation of flow visualization. This concept emphasizes the important difference between steady and unsteady flows.
Smoke streakline visualization. The flow behind a cylinder shows a periodic vortex shedding pattern. Near the cylinder, the streaklines appear chaotic due to strong vortex release. Farther downstream, the flow pattern becomes smoother and more organized. The streaklines represent the time-integrated motion of the fluid. This example shows how the flow structure evolves from the near body region to the far field.
Check your understanding. Number 6. What does the streakline pattern downstream of a circular cylinder primarily represent? Correct answer, C. The transition of fluid flow from chaotic near-cylinder regions to smoother, organized patterns farther downstream. Explanation of incorrect options. Option A. Streaklines represent the path of fluid particles over time, not instantaneous velocity vectors, which are shown using vector diagrams. Option B.
While vortex shedding causes the streakline patterns, streaklines do not directly depict pressure differences, they visualize the resulting flow. Option D, streaklines are not related to density variations or compressibility effects, they focus on visualizing fluid motion and patterns over time.
Kármán vortices in clouds. Kármán vortex patterns can be observed even at the atmospheric scale behind an island. Clouds act as natural tracers that clearly reveal the vortex structures. These vortices are formed periodically due to flow instability behind an obstacle. This phenomenon shows that the same concepts apply from laboratory scale to natural scale. This example emphasizes the universality of fluid mechanics. Comparison of flow lines. Streamlines show the instantaneous flow direction at a given time. Path lines show the actual trajectories of particles over a time interval. Streak lines show the locations of all particles released from the same point. In unsteady flows, these three lines are generally different from each other. This comparison is important to avoid misinterpretation of flow visualization. Timelines in fluid flow. A timeline is formed by marking a line of fluid particles at an initial time. As time progresses, this line changes shape due to a non-uniform velocity field. This deformation reflects the presence of velocity gradients and flow distortion. With timelines, stretching and distortion of the flow can be visually observed. This concept helps in understanding fluid element deformation. Check your understanding. Question number 7. An initial marker line, known as a timeline, changes shape over time as fluid particles move and interact with the flow, providing insights into velocity gradients and distortion within the flow field. Boundary layer visualization. The hydrogen bubble method is used to visualize the velocity profile near a wall. The bubbles show how the near-wall flow becomes unstable. As the distance increases, these disturbances grow and lead to transition to turbulence. The timelines reveal strong velocity gradients within the boundary layer. This example shows how kinematics is used to study boundary layer development. Bow wave and shock dynamics. A sphere moving at supersonic speed forms a shock wave in front of it. This wave appears because the fluid cannot adjust gradually to such a high-speed disturbance. The dark region in the image indicates locations of very sharp changes in pressure and velocity. This phenomenon is characteristic of compressible flows at high Mach numbers. This example shows the fundamental difference between subsonic and supersonic flows. Natural convection visualization. Schlieren imaging is used to visualize hot air rising due to temperature differences. The rising plume patterns show the presence of buoyancy forces caused by density variations. This flow occurs without any fan or external forcing. This phenomenon is called natural convection and is very important in many engineering applications. This visualization shows how heat transfer can drive fluid motion. Boundary layer velocity profiles. The velocity profile shows that the fluid velocity is 0 at the wall and increases away from the surface. The shape of this profile changes along the flow direction as the boundary layer grows thicker. The velocity gradient near the wall indicates the presence of shear stress. This representation is very important for understanding friction and energy losses.
The velocity profile is one of the most important kinematic descriptions in fluid mechanics.
Check your understanding. 88.
What does the velocity profile in a boundary layer over a flat plate primarily represent? Correct answer, B. The increase in horizontal velocity with vertical distance from the plate, showing the development of shear effects. Explanation of incorrect options. Option A. The velocity profile does not directly represent pressure variation. It specifically shows velocity changes due to shear effects and boundary layer growth. Option C. Density and temperature changes are not the focus of velocity profiles in boundary layers, which highlight velocity gradients and shear effects instead. Option D. The boundary layer introduces non-uniform velocity distribution near the plate, making this option incorrect. Uniform velocity only occurs far from the plate, outside the boundary layer.
CFD flow impingement on block. The CFD result shows a recirculation region behind the block due to flow separation. Velocity vectors illustrate how the direction and magnitude of the flow change around the object. In front of the block, the flow slows down and then separates. Behind it, rotating eddies are formed. This example shows how numerical visualization helps in understanding complex flow structures.
Pressure field around block. The color contours show the pressure distribution around the block. High pressure appears at the front, where the flow is brought to rest. Behind the block, the pressure becomes lower due to the wake and flow separation. The contour lines help visualize pressure gradients quantitatively. This example links flow kinematics with the pressure field. Fluid element motion types. The motion of a fluid element can be decomposed into translation, rotation, and deformation. Translation means the element moves without changing its shape or orientation. Rotation means the element spins like a rigid body. Deformation includes shape changes due to stretching and shear. This decomposition helps analyze fluid motion in a systematic way. Fluid element rotation. The average rotation is defined from the change in orientation of two initially perpendicular lines. This rotation occurs simultaneously with the deformation of the fluid element. Its value is defined locally at a point in the flow. This concept is important to distinguish rigid body rotation from shear deformation. From here, the concept of vorticity is later derived. Linear strain rate. The linear strain rate measures the rate of change of length per unit length in a specified direction. A positive value indicates extension, while a negative value indicates compression. This definition is based on very small changes in time and distance. This concept is important for analyzing how a fluid element stretches or shortens. It is one of the main components of fluid deformation.
Check your understanding. Number 9. The strain measures the rate of change in length per unit length in a specified direction, with positive values indicating extension and negative values indicating compression. Volumetric compression. The piston motion causes the volume of the air element to decrease gradually. This volume reduction is called negative volumetric dilatation. When the volume decreases, the pressure inside the fluid element increases. This phenomenon shows the direct relationship between volume change and pressure. This concept is important for understanding compressible flow behavior. Shear strain rate.
The shear strain rate measures how fast the angle between two initially perpendicular lines changes. This angle change indicates distortion of the fluid element shape. Its value is proportional to half the rate of change of that angle. This concept is different from linear strain, which changes length. Shear strain is mainly associated with shape change without volume change.
Fluid element deformation. In real flows, a fluid element usually experiences translation, rotation, and deformation simultaneously. Linear strain causes the element to stretch or shorten. Shear strain causes shape change without changing volume. Volumetric strain causes a change in the element volume. The combination of all these effects describes the full dynamic behavior of a fluid element. Streamlines and stagnation point. The streamline pattern shows how the flow bends and splits around a certain point. The stagnation point is the location where the flow velocity becomes zero. Around this point, the flow direction changes significantly. The pressure at the stagnation point usually reaches a local maximum. This concept is very important in aerodynamics and flow around bodies. Check your understanding. Number 10. Where does the flow velocity become zero in the flow field, as illustrated by a red circle in streamline patterns? Answer: B. Stagnation point. Explanation: A. Divergence point. This is incorrect because the divergence point refers to regions where the flow lines are spreading apart, not where the velocity is zero. B. Stagnation point. This is the correct answer, as the stagnation point is where the flow velocity becomes zero, typically marked by a red circle in streamline patterns. C. Convergence point. This is incorrect because convergence refers to points where the flow lines come together, but the flow velocity does not necessarily become zero. D. Velocity node. This is incorrect because a velocity node is not a standard term used in flow analysis. It does not specifically refer to the zero velocity point as described in the question. Fluid parcel deformation. A fluid element that is initially square can change into a rectangular shape. This change is caused by a combination of stretching and shear in the flow field. Near a stagnation point, the deformation can become very significant. Streamlines help show how this element moves and changes shape. This example illustrates the concept of deformation visually. Right-hand rule for cross product. The right-hand rule is used to determine the direction of the cross product of two vectors. The fingers are aligned with the first vector and curled toward the second vector. The thumb then points in the direction of the resulting vector. The cross product result is always perpendicular to both original vectors. This rule is very important in vector analysis in fluid mechanics. Vorticity in rotating fluids. Vorticity represents a measure of the local rotation or circulation of a fluid element. By definition, its value is equal to twice the angular velocity of the element. This quantity is used to identify regions of rotational flow. Vorticity is very important in the study of turbulence and aerodynamics. With vorticity, the rotational nature of a flow can be analyzed quantitatively. Rotational versus irrotational flow. Inside the boundary layer near the wall, fluid elements rotate and have vorticity. Outside the boundary layer, the flow can often be considered irrotational. The velocity profile shows the transition from the no-slip condition at the wall to the free stream. This division is very important for simplifying flow analysis. This concept forms the basis of potential flow and boundary layer theory.
Check your understanding. Number 1. In the rotational region, fluid elements rotate within the boundary layer, close to the wall, creating vorticity.
Two-dimensional flow and vorticity. For two-dimensional flow in the xy plane, the vorticity vector is always aligned with the z-axis. The direction of vorticity indicates the direction of fluid particle rotation. Counterclockwise rotation produces vorticity in the positive z direction. This concept simplifies the interpretation of the vorticity sign in two-dimensional analysis. In this way, rotational information can be represented in a simple form.
Vorticity contour in flow. The color contours show regions of strong positive and negative vorticity. The interaction of the flow with the block creates rotational regions around it. Red and blue colors help distinguish opposite directions of rotation. This pattern reveals complex flow structures around a bluff body. This visualization is very helpful in numerical and experimental analysis.
Vorticity in r-theta plane.
In cylindrical coordinates, the direction of vorticity remains perpendicular to the flow plane. Clockwise rotation produces vorticity in the negative z direction. This representation simplifies the analysis of two-dimensional flows in circular geometries. This concept is often used in the analysis of vortices and swirling flows. In this way, the sign and direction of vorticity can be clearly determined.
Rotational flow and deformation. A fluid element can undergo rotation and deformation at the same time. An initially square shape will change its shape and orientation over time. Streamlines show how the element is carried by the flow. The longer the time, the greater the shape change becomes. This example shows that rotation does not mean the fluid element remains undeformed. Rotational versus irrotational flow. A rotational flow, such as solid body rotation, has tangential velocity that increases with radius. An irrotational flow, such as a line vortex, has velocity that is inversely proportional to the radius. Although both have circular streamlines, their physical nature is very different. This difference is very important in modeling vortex flows. This example clarifies the difference between true rotation and potential flow.
Check your understanding. 12. Which of the following describes a flow where velocity is inversely proportional to radius and exhibits irrotational flow except at the origin? Answer: B. Flow B. Explanation: A. Flow A. This is incorrect because flow A represents solid body rotation, where the tangential velocity increases with the radius, not inversely proportional. B. Flow B. This is the correct answer, as flow B is described as a line vortex with irrotational flow, where the velocity is inversely proportional to the radius, except at the origin. C. Solid body rotation. This is incorrect because solid body rotation involves increasing velocity with the radius, which does not match the characteristics of flow B. D. Circular streamline flow. This is incorrect because circular streamlines are found in both flows, but the question is asking about specific characteristics like the velocity distribution, which differs between the rotational and irrotational cases.
Circular flow analogy. The roundabout and Ferris wheel analogies are used to distinguish rotational and irrotational flows. Rotational flow resembles a roundabout where all elements rotate together. Irrotational flow resembles a Ferris wheel where motion occurs without local element rotation. This analogy helps build physical intuition. With simple visuals, the conceptual difference becomes easier to understand.
Streamlines of a line sink. The streamlines show flow moving radially toward a central point. This pattern represents a line sink in a two-dimensional plane. All particles move straight toward the center from different directions. This representation is often used in potential flow analysis. This example shows how a simple flow field can be described analytically.
Analysis of spray can. The system approach tracks the fluid mass as a moving entity. The control volume approach observes the flow crossing a fixed region. In the spray can case, mass leaves through the control volume boundary. The two approaches provide different but complementary perspectives. This example serves as an introduction to the Reynolds transport theorem.
Reynolds transport theorem. The Reynolds transport theorem serves as a bridge between the system and control volume approaches. This theorem allows the calculation of changes in mass, momentum, and energy within a control volume. With this theorem, conservation laws can be applied to open systems. This concept is very fundamental in engineering fluid mechanics. Almost all practical flow analyses use the RTT framework.
Check your understanding. 13. The RTT, Reynolds transport theorem, method links the system and control volume approaches in fluid flow analysis, enabling tracking of mass, momentum, and energy across control volume boundaries. Control volume and system. RTT. A control volume is a fixed region in space through which fluid flows. A system is a collection of fluid particles moving with the flow. The upper and lower boundaries of the control volume can be defined by streamlines. RTT links the change of system properties with the flow across the control volume boundaries. This representation helps visualize the difference between the two approaches. Net flow in control volume. Control volume analysis accounts for the flow of mass and properties entering and leaving through the control surface. Surface integrals are used to compute the net outward flux. The direction of the outward normal vector determines the sign of the flow contribution. With this approach, mass, momentum, and energy balances can be written in a general form. This concept forms the basis of all control volume-based conservation equations. Mass flow analysis. Outflow occurs when the velocity vector makes an angle less than 90 degrees with the outward normal. Inflow occurs when the angle is greater than 90 degrees. If the velocity vector is perpendicular to the surface, there is no flow across that surface. This rule helps determine the sign in mass flux calculations. This concept is important for consistency in mass balance analysis. Relative velocity concepts. Relative velocity is defined as the difference between the absolute fluid velocity and the control surface velocity. This concept is important when the control volume is moving or deforming. The relative velocity determines how fast the fluid actually crosses the control surface. With this approach, flow analysis in moving systems becomes simpler. This concept is widely used in the analysis of turbines, pumps, and moving vehicles. Control volume in motion. In the absolute frame, the flow is observed relative to the ground or a fixed reference. In the relative frame, the observation is made from the perspective of a moving control volume. The relative velocity is obtained by combining the flow velocity and the reference frame velocity. This approach is very important for analyzing jets, rockets, or moving vehicles.
By choosing the appropriate frame, the analysis becomes much easier. Check your understanding. Number 14. Which of the following describes the perspective where fluid flow is analysed relative to a moving control volume, such as the car's frame? Answer B. Relative frame. Explanation. A. Absolute frame. This is incorrect because the absolute frame involves observing fluid flow relative to a stationary reference, such as the ground, not a moving control volume. B. Relative frame. This is the correct answer, as the relative frame shifts the perspective to a moving control volume, such as the car's frame, where velocities are adjusted based on the movement. C. Ground reference frame. This is incorrect because the ground reference frame is stationary, akin to the absolute frame, and does not involve a moving control volume. D. Stationary frame. This is incorrect as well, as the stationary frame also implies a fixed reference, not a moving control volume, like the relative frame.
Control volume with one inlet and multiple outlets is commonly found in engineering systems. For simplification, surface integrals can be replaced by average flow values. This approach makes the RTT equations easier to use in practice. Even though it is simplified, the physical meaning remains the same. This example is very common in the analysis of pipes, nozzles, and diffusers. Leibniz theorem in time derivatives. The Leibniz theorem is used to compute the time derivative of an integral with time-varying limits. This concept is important for systems with moving or changing boundaries. With this theorem, changes in the integration domain can be systematically accounted for. This is the mathematical foundation of the Reynolds transport theorem. Without this concept, the formal derivation of RTT would not be possible. 3D Leibniz theorem. The three-dimensional Leibniz theorem extends the concept of time derivatives to volumes that deform or move. This theorem accounts for changes in the boundaries of a volume in three-dimensional space. This concept is very important for analysing non-fixed control volumes. With this approach, changes of integrated properties within a volume can be computed consistently. This is one of the main mathematical foundations of the Reynolds transport theorem. Material versus control volume. At the initial time, the material volume and the control volume may coincide. As time progresses, they move and deform in different ways. The material volume always follows the same fluid particles. The control volume is defined in space or moves according to the analyst's choice. This difference explains why a linking theorem, such as RTT, is needed. RTT viewpoint transformation. RTT allows the transition from the Lagrangian to the Eulerian viewpoint. This theorem also links the integral form to the differential form of conservation equations. With RTT, system analysis can be converted into control volume analysis. This makes the application of conservation laws much more practical in engineering. This slide summarizes the conceptual role of RTT in fluid mechanics. Check your understanding. The Lagrangian to Eulerian transition shifts from tracking individual particles to analyzing control volumes in fluid flow analysis. References. This section lists the main source of figures and material, namely the book by Chengle and Chimbala. This reference is one of the standard textbooks in engineering fluid mechanics. By listing the reference, the clarity of scientific sources is maintained. This is also important for academic ethics and further reading. This chapter as a whole follows the framework and illustrations from that reference.